Survey of Calculus, Chapter 2, Section 4, using derivatives to find absolute maximum and minimum values. First, a definition. Suppose that f is a function with domain I. F of c is an absolute minimum if f of c is less than or equal to f of x for all x in I, and it's an absolute maximum if f of c is greater than or equal to f of x for all x in I. In other words, an absolute minimum is the absolute lowest point on the graph. Now, you can have more than one if they're on the same level, they're at the same y value. You can have more than one. The value itself, the y value, is the minimum. The x is just the location. An absolute maximum, by the same token, is the absolute highest point, highest y value belonging to that function. And that's what makes them absolute. Notice this is over the entire domain of the function. Relative maximum and minima occur over, they're the highest or lowest within an interval. The absolutes are highest or lowest within the entire. First, we have an extreme value theorem. It says that a continuous function, f, defined over a closed interval, a to b, must have an absolute maximum value and absolute minimum value over ab. So in other words, if your function is continuous over a given interval, then it has to have an absolute and it has to have an absolute minimum. Theorem 8 tells us that, let's say f is a continuous function. It's defined over a closed interval, a to b. To find the absolute maximum and minimum values, what we need to do is first find the first derivative. Then we'll find all of the critical values in AB. Now, that should not be a big surprise because that's how we've been finding our relative maximums and minimums. So find all of the values in AB where the first derivative is 0 or does not exist. And what we're going to do is we're going to list those values, but also include the endpoints of the interval because our maximum or minimum values could possibly be the beginning or the end of the interval. So we want to include those as well. So we list all of those x values, the beginning of the interval, all of the x values that were 0 for the first derivative, and then the end of the interval, all of those x values. Then we're going to find all the y values that match. That's part D. And the largest of all these y values will be our maximum, and the smallest will be our absolute minimum. So kind of makes sense. All right, let's try an example. We're going to do what we just talked about. You're going to find the absolute maximum and minimum. So you're going to set the first derivative, you're going to take the first derivative, set it equal to 0. List the values of x that give you 0 for that first derivative, along with -2 and 3/2, the beginning and the end of our interval, and then find the y values that match. Pause the recording, give this a try, and resume to check your answer. Okay, so our first derivative is 3x squared minus 3. The function exists for all real numbers, and we're going to, that means we don't have to worry about something not being in the domain here. Solve for the first derivative equal to 0, and we get positive and -1. So we're going to check -2, -1, 1. Okay, so here we've listed our endpoints and our critical points, or our values for x. We put them all into the function and got the y values. And we can see that we have a maximum, an absolute maximum, when x is -1, y is 4. That'll be our absolute maximum. We actually have two absolute minimums, and that value is 0, and it occurs in two places, at -2 and at 1. Now try to find the absolute maximum and minimum values for that function we just did. So you already have the derivative taken and everything. And we already have the critical values. This time you're going to use 0 and 3 for your endpoints. So pause the recording, give this a try, and resume to check your answer. Okay, so there was our function and our first derivative and our values. So we're putting those and the new endpoints in. And actually we don't need to consider -1 because our we really could kind of kick -1 out of there because our two endpoints are 0 and 3. So the f of -1, even though I've got it in there, doesn't really matter. What matters is 0, 1, and 3, because the interval was from 0 to 3. The absolute maximum is 20, and that occurs when x is 3, and the minimum is 0 when x is 1. Theorem 9 is the second maximum minimum principle, and it says, suppose that f is a function and that the first derivative exists for every x in an interval I, and that there's exactly one critical value where the derivative equals 0. In other words, the last one we had two values where the derivative was 0. This time we only have one within that interval. Okay? Then f of c is the absolute maximum value over the interval if the second derivative is negative, or it's the absolute minimum value if the second derivative is positive. In other words, if you come away with only one critical value, then you can use the second derivative test to see if it's going to be positive or negative, which will tell you if it's a maximum or. Okay, so find the absolute maximum and minimum values of this function. Pause the recording, give it a try, resume to check your answer. Okay, they didn't give us an interval, so you need to consider the entire domain of the function. In this case, we're going to use the set of all real numbers. So if you were kind of puzzled by, well, what's my interval, and need to pause now that you know this and try again, go ahead and do that. If not, we'll continue with the explanation. So we're going to use the set of all real numbers. First, take the derivative, and we get 4 minus 2x. Set it equal to 0 and solve. And very simple math here. We have x equals. Okay, so we only have one critical value, and we can use the principle 2 that we just talked about. The second derivative is negative regardless of what x is. It's -2. So that means that since the second derivative is negative, it's concave down, which means we have a maximum. So our x value of 2 gives us a y value of 4, and that point gives us our absolute maximum. So the function has an absolute maximum value of 4 at x equals 2 and has no absolute minimum value. Okay, try this one. We've got one equation, two different intervals. Try the principles we've just talked about. Pause the recording, give it a try, and resume to check your answer. All right, looking at the function, we can see that the absolute minimum over the entire domain over all real numbers is -25, and it's located at x equals 5. This is just using what you know about functions. This is a parabola, x squared minus 10x. And so we have an absolute minimum. It's concave up, it opens up, it's a parabola. And so it has an absolute minimum, and that's going to occur when x is 5. And we're kind of shortcutting it here a little bit. 5 is in both the interval from 0 to 6 and 4 to 10. So the absolute minimum at both of those is going to be -25 located at x equals 5. We do need to check the endpoints and see which, if either, would be an absolute maximum. So we know the minimum, but we do need to check the maximum. So we take the endpoints of each interval and we put them into the original function. And for a, when we put in 0, we get 0. When we put in 6, we get -24. So our absolute maximum is going to be 0 and is located at x equals 0 for a. For b, we do the same thing, and we find that our absolute maximum is 0, and it's located at 10. So we really didn't even do any calculus with that problem. That was just kind of using what we know about graphs and about the way parabolas work. Okay, so now we're going to talk about a strategy, or kind of put this all together to find the absolute maximums and minimums of a function, of a continuous function over an interval. First of all, find the first derivative. Find the critical values. If the interval is closed and there's more than one critical value, use the maximum minimum principle 1. In other words, you're going to list the critical values, you're going to list the endpoint, what the y values are. and use that to determine your absolute max and min. If the interval is closed and there's only one critical value, then you can either use that principle or you can check the second derivative and see if it's going to be a maximum or a minimum by its concavity. If it's not closed, if it's negative infinity to infinity, or it's just an open interval, and the function has only one critical value, then you can use, again, principle 2. You can find the second derivative and see if it's positive or negative. In such a case, if it has a maximum, it will have no minimum. If it has a minimum, it will have no maximum. Because remember, again, our critical values are where the maximum will occur, if they're going to occur, unless we have a closed interval. In that case, it could occur at the endpoints. But here we're talking about an interval that's open, that's not closed. It doesn't have definite endpoints. So the critical value we find will be the only extreme value, the only maximum or the only minimum. Okay, give this a try, pause the recording, and resume to check your answer. Okay, so taking the first derivative, we get 5 minus 35 over x squared, or you may have gotten 5 minus 35x to the minus 2. The advantage to putting it over x squared is to remind us that that is a place where the derivative does not exist. Since the derivative exists for all values of x in 0 to infinity, the only critical values are where the derivative equals 0. So 0, we can't have 0 because it would be a denominator, but it's okay because it's not in the interval for which this is defined. Okay, so here you see that we have solved for where the first derivative equals 0. We get plus or minus square root of 7. However, negative square root of 7 is not in the defined interval. So the only critical value we have is the square root of 7, and then you can use the second derivative and check it and see if this is an absolute maximum or minimum. And here we're doing that. So we have the second derivative is 70 over x to the third, or 70x to the minus 3. Putting in the square root of 7, we discover, and really we don't care what it is, we just want to know if it's positive or negative. It's positive, so you don't really have to get a number for that. So it is positive, which tells us it is going to be concave up, which means it's a minimum, is an absolute minimum, and then we're going to find the y value that matches, and when we do that, we get 10 square root of 7. Now try this problem. Pause the recording, give it a try, and resume to check your answer. Okay, so we're going to find the derivative of g of x. Now here we used the quotient rule. You could have rewritten it as 2x squared over x plus 18 over x, which would have given you 2x plus 18x to the minus 1, and then just taken the derivative of that. Notice that we did do a little simplifying here, and that was mostly just to make it easier to work with. You don't necessarily have to do that, but it's going to make it easier. So we want to set it equal to 0. And here we're doing that. When we solve, we get plus or minus 3. Now, negative 3 is not in the interval, so there is a critical value at. We apply the maximum minimum principle, and we get that it is indeed positive, so it is concave up, so it is a minimum at x equals 3, and the value when x is 3 is 12, and that is our minimum, our absolute minimum. And here's our summary. You may want to pause and look over this, and then resume to continue on to additional practice problems. Okay, these are some more practice problems. If you will work on these, pause while you're doing that, resume to check your answer, and then continue until the end of the recording.